Hello, welcome to Astronautics for Exploit. This is Dr. Ayoshola Ogundele. Solar cells, the future of space exploration, having capability of using sun's energy indefinitely to propel spacecraft into deep space. The focus points are as follows: solar cells, types of solar cells, advantages of solar cells, and solar cells operations. For many years, solar cells concept has been depicted in several science fictions. In 1964, author Clarke and Poul Anderson independently published stories titled Sunjammer that featured the concept of solar cells. In 2002, Star Wars film Attack of the Clones, the main villain, Count Dooku, used a spacecraft with solar cells. In the Avatar epic science fiction film of 2009, which was set in the mid-22nd century, when humans colonized Pandora, a loose habitable moon of a gas giant in the Alpha Centauri star system, in order to mine the valuable unobtanium, a room-temperature superconductor mineral. Solar cells were used as means of propulsion to accelerate the vehicle away from the Earth towards Alpha Centauri. Solar cell, a concept of spacecraft propulsion, also known as light cell or photon cell, uses the pressure of sunlight for propulsion, angling toward or away from the sun so that photons bounce off the reflective cell to push a spacecraft forward. In comparison to the conventional rocket propulsion, which relies on burning fuel and ejecting it at high speed to create thrust, solar cell concept eliminates the need for heavy propulsion systems and has the potential to enable longer duration and lower cost emissions. Unlike the rocket propulsion, which is limited by the amount of fuel that it can carry on board, which determines how far and how fast the spacecraft can go, solar sailing does not need any fuel and can use the sun's energy indefinitely as long as the sail is intact and oriented correctly. Solar cells, also referred to as light sails, are a method of spacecraft propulsion using radiation pressure exerted by sunlight on large surfaces, such as large mirrors, to push the spacecraft through space. Since 1980s, several spaceflight missions to test solar propulsion and navigation have been proposed. The first spacecraft to make use of the technology was Icarus, launched in 2010. The picture here illustrates Icarus, the first space probe with a solar cell in flight. Solar cell spacecraft offers the possibility of low-cost operations combined with high speeds in comparison to chemical rockets and long operating lifetimes. Since solar cells spacecraft have few moving parts and use no propellant, they can potentially be used numerous times for the delivery of payloads. Solar cells designed to capture the momentum from solar energy photons using large mirrored surface is illustrated in this picture. Solar cells are made of lightweight, reflective material, just a few hundred nanometers thick. When sunlight strikes the cells, photons transfer momentum to the cell, creating a small but continuous thrust. Solar cell uses photons from the sun to propel a spacecraft. The photons are massless and carry energy and momentum, allowing a small but continuous pressure to be generated, which can move a spacecraft without the need for fuel. Artist's concept of nanocell D in space is shown in this picture. Types of solar cells. There are different types of solar cells, such as square cells, transmissive cells, diffractive cells, and electric cells. Square cells generate higher force than average solar cells due to the large surface area. They are composed of four masks which are then deployed into space. Advantage of square cell over other cells is that there are no hot spots because the cell protects the spacecraft from the sun's thermal heat. Light cell 2 illustration is shown in this picture. Transmissive cells are advantageous in every flight regime. They improve solar cell performance and operational flexibility. Non-metal transmittive cells are advantageous at low altitude and high inclination. Diffractive cells are a type of solar cell which relies on diffraction instead of reflection for its propulsion. Current diffractive cell designs use thin metamaterial films containing micrometer-sized gratings based on polarization or subwavelength refractive structure. Concept art for a diffractive light cell is illustrated in this picture. Reflective cells. Most solar cells are based on reflection. The surface of the cell is highly reflective, like a mirror, and light reflecting off of the surface imparts a force. Electric cells ride on the solar wind, which is charged particles ejected by the sun. Near-Earth asteroid scout, a 2014 mission concept by NASA to analyze, design, develop, and fly a controllable, low-cost CubeSat solar cell, is illustrated in this picture. Advantages of solar cells. Solar cells have the following advantages: continuous propulsion, fuel-free operation, cost-effectiveness, deep space exploration, and eco-friendly. Without the need for chemical fuel, solar cells offer an environmentally friendly alternative to traditional propulsion methods. They produce no harmful byproducts and rely entirely on the abundant natural energy provided by the sun. Illustration of advanced composite solar cell system is shown in this picture. Cost effectiveness. Elimination of fuel from the spacecraft payload significantly reduces the launch and operational cost. Additionally, the simplicity of solar cells could lead to lower manufacturing and maintenance expenses compared to more complex propulsion systems. Solar cells are particularly suited for missions that go beyond the inner solar system. Concept image of the Okeanos mission is illustrated in this picture. Continuous propulsion. Ability to provide continuous propulsion. Unlike conventional rocket engines, which burn fuel in a short, powerful burst, solar cells generate a steady, much weaker thrust over a long period. This allows a spacecraft to gradually build up significant speed. Solar cells require no propellant, making them an ideal choice for long-term missions where carrying sufficient fuel will be impractical. Illustration of Sunjammer solar cell is shown in this picture. Solar cells operations. Solar celling operations involve using sunlight to propel a spacecraft by changing the angle of a reflective cell relative to the sun. The cell's operations include changing orbits, swing-by maneuvers, parking, and controlling direction. The cell's orientation relative to the sun can change the spacecraft orbit. For swing-by maneuvers, a close path to the sun can increase the spacecraft energy. NASA's solar cell system is illustrated in this picture. The cell's angle can change to move the spacecraft in different directions, and the cell center of mass or thick veins can be used to control its direction. Illustration of solar cruiser is shown in this picture. Working principle of solar cells. The sun emits photons, which are particles of light with no mass but momentum. When photons hit the cell, they transfer some of the momentum to the cell. The cell pushes the spacecraft in the opposite direction of the sun. The spacecraft accelerates and eliminates the need for rocket propellant. An artist's concept of a breakthrough starshot spacecraft in action is illustrated in this picture. For more information, contact Astronautics for Experts. You've been watching and listening to Solar Cells, the Future of Space Exploration, having capability of using sun's energy indefinitely to propel spacecraft into deep space. Presented by Dr. Ayeshola Ogundele, with focus points: solar cells, types of solar cells, advantages of solar cells, and solar cells operations. Thank you.